So, we will continue with properties of the harmonic functions. Okay, it will take some more time before we can get into some Fourier analysis, but let's do a quick recap of what we have proved. Okay, so that you are on the same page. So, remember we started with harmonic functions. So, U is harmonic if delta U is 0. So, what was delta? Delta was the Laplacian, right, summation d square by dxj square, right. So, this was delta j equal to 1 to n. So, everything is happening in some domain in Rn. Okay. So, the first thing we proved was this implies U satisfies mean value property, right. That is the first thing we proved, right, if you remember Green's theorem and all that. Well, what does this mean? This means you take any point A and look at a sphere of radius r centered at A contained in D, then the mean value of U over this sphere, so that is written as U of A r omega d sigma omega, this is the value at the center, right. Okay. This, as I said, polar coordinates, in polar coordinates, this immediately implies the ball mean value property. Okay. So, ball mean value property is, so now you look at not the sphere, you look at the ball of the solid ball of radius r, so and look at the Lebesgue measure of that. So, dividing by the total measure is called the mean value, right. The average means you take the integral over the ball now instead of the sphere, uy dy. This is the usual Lebesgue integral over a ball for a function, right, and this is u of a, right. So, these two are sort of equal, okay, if and only if differentiate, if you have enough radius and so on, differentiating this will give me this, integrating this will give me this. Okay. So, it is I'll leave it to you to figure out why these two are sort of same. Write this in polar coordinates, differentiate, you will get this, and do the other way, you will integrate this, you will get. In other words, the integrals over the sphere is the derivative of integrals over the balls. Okay. All right. So, whenever U is harmonic, you have all this, and then we showed that if U satisfies the mean value property, then U is harmonic, right. So, this was one way. In the other way, we proved that if U is continuous, right, and U satisfies the mean value property, then U is harmonic, right. So, U is infinity and harmonic. Okay. So, that is an extra thing we obtain. Here we did not say that, right. Here harmonicity means delta U is 0 and this requires only U is twice differentiable, right. So, let us say C2, and here at no place we said U is infinity, but the moment U satisfies mean value property, we know U is infinity, right. So, any harmonic function is a C infinity function, it is actually real analytic, but that is a different theorem. So, it is more than C infinity, but it is at least C infinity because the mean value property is satisfied. From continuity you can go to locally integrable. So, if U is locally integrable and U satisfies, okay. So, now comes the ball mean value property, because this is a set of measures 0. So, this formula does not make sense, right. You can change U on a set of measures 0 always. So, you will not get this formula. For whenever you deal with L1 spaces, LP spaces, there is an almost everywhere statement comes in. So, it is always safe to integrate over a ball. Okay. Here changing U on a set of measure 0 will not change anything, right, because the integral will not change. Okay. So, if it is locally integrable and U satisfies ball mean value property, then U is infinity. Now, once U is infinity, it does not matter whether you are integrating over Sn minus 1 or this, right, because you can go to the other by differentiating, and so it will satisfy the sphere mean value property, and so it is harmonic and harmonic. Okay. So, this is what we did so far. Okay. Well, so let's continue with the next one. So, this is a theorem you already know. So, it's called Liouville's theorem. Okay. So, you have seen Liouville's theorem for holomorphic functions, right? Entire functions which are bounded is a constant, right? Here you will have harmonic functions which are bounded, on the whole Rn will be a constant. If u is harmonic, on Rn, now, right, our functions are defined on Rn. For holomorphic functions we have entire functions, here they are defined on the whole space, right, that is what we need. And bounded, if u is harmonic and bounded, then u is a constant. U is a constant. Bounded harmonic functions defined on the whole space Rn are constants, right? Bounded entire functions are constants. So, that is the analogy with complex analysis. Okay. Well, there it happens because the entire functions are harmonic. Okay. That is the reason. So, proof. So, well, you know u is harmonic, right. So, u satisfies the mean value property, and so u satisfies the ball mean value property, right. So, u satisfies the ball mean value property. So, we use that. Okay. Well, how do we use that? Let us take 2 points, let x1 and x2 be 2 points, 2 points in Rn. Okay. I want to say u is a constant, which means u x1 is equal to u x2, right, that is enough, right. If I take 2 arbitrary points and say that u has the same value at those 2 points, then u is a constant, right. So, enough to show that. So, this is what we will be proving, enough to show that u of x1 is equal to u of x2, right, because the x1 and x2 are arbitrary parts. Okay. So, for that we use the ball mean value property. Okay. So, we write down, so let us draw some pictures. So, I take x1 here, okay, and I have let us say x2 here. We look at balls around x1 and x2, write down the mean value and see what happens to the difference, right. So, let us you can use the ball of radius, let us say t, okay. Okay, this will not intersect. So, I want them to intersect. So, let's draw the picture, the points closer by, so that they will intersect. So, let us say x2 is somewhere very close here, okay. And I look at a ball of radius t around this, okay. So, same radius, okay, it does not look like, but they are. Now, I integrate over these balls, right, though that is a ball mean value property. So, I can write ux1 minus ux2 as ux1 I write as an integral over this ball, and similarly ux2 I write as an integral over this ball. Radius is same, okay. So, I will have 1 by b x1 t, right, t is the radius, okay, modulus of that, which means the Lebesgue measure, integral over b x1 t uy dy minus, right, that is the ball mean value. Similarly, at x2, 1 by mod b x2 t integral over b x2 t uy dy, all right. So, I have used only the ball mean value property, right, that characterizes your harmonic function. Now, well, what is bx1 t? This is the volume of the ball of radius t centered at x1. Similarly, this is centered at x2, but these two are same, right. So, that is t to the n times some constant. So, that comes out, right. So, I can write this as, So, I will write this as the ball around 0. Okay. So, 1 by mod b 0 t. So, that is like t to the n, right. Integral over b, this cannot be changed x1 because I am integrating, right, u I dy minus integral over bx2 t u I dy. Okay. So, I have not done anything highly non-trivial except observing that these two are same and then taking it out. Well, what is that integral? I am integrating over this ball and subtracting integral over this ball, right. So, this guy will go away, right, that is a common portion, right. So, whatever remaining here you will be integrating over this and you will be integrating over whatever is here, correct. That is the symmetric difference between these two sets, right. So, this is simply 1 by, so this is something like some constant times t to the n, okay. Integral over ball of x1 t symmetric difference ball of x2 t, right. What is the symmetric difference? A minus b union b minus a, right. So, this minus this portion will be this and this ball minus whatever is here would be this, right. That is the integral you will be looking at, u I dy, right. The same function you are integrating. Now, well, what are we assuming? We are assuming u is bounded, okay, and I want to say u is a constant using this, right. So, let us start with taking the modulus. So, modulus of u of x1 minus u of x2 now would be less than or equal to 1 by some constant Cn t to the n. Well, when I take the modulus inside, I have mod u, but u is bounded. So, I can take the supremum of u outside, right. So, I will put that here. So, that is L infinity norm of u, right, that is the supremum of u over Rn, right, it is bounded on the whole of Rn. So, the modulus here and I take it outside, what remains is the measure of this, right. So, measure of Bx1 t symmetric difference between x2 t, right. So, that is the measure of whatever is here, right. So, measure of this portion, right, this is not included. But what will happen? So, this is true for all t, right. Now, we are on Rn. So, we can take as large as balls you want, right, we do not go out of the domain. So, as t becomes larger and larger, what will happen to these two balls? They become same essentially, right. So, whatever is outside becomes smaller and smaller. So, it goes to 0, but of course, you have to prove that, okay. So, this goes to 0 as t goes to infinity, okay. So, that you can check, you can actually estimate this integral. So, I will tell you why on the real line. Let us look at what happens on the real line. 0. So, let us take 2 points, right, 0 and 1, okay. And I have ball of radius t around one point and ball of radius t on the other point, right. So, what is the ball of radius t around 0? That will be from minus t and t here, right. So, this is one ball, right. Ball around 1 would be 1 minus t to 1 plus t, okay. So, let us say 1 minus t here and 1 plus t here, okay, this one, right. What is the symmetric difference? Whatever is here, right. What is the measure of that? What is the measure of this? Okay, I should have taken a simpler example. Maybe 0, 1. Let us take larger balls, right. So, minus n to n, and this would be minus n plus 1 to n plus 1, right. So, symmetric difference is this, Okay. So, we will just take t to be n. Okay. So, minus n to n is the ball around 0, minus n plus 1 to n plus 1 is the ball around 1. Symmetric differences between this and this, right? Everything else is common. The measure of this is 1, the measure of this is 1. So, measure of the symmetric difference is 2, right? And we are dividing by measure of ball of radius n, that is just n. So, it is 2 by n, and that will go to 0 as n goes to infinity, right? That is what you have to show. Okay. So, you can actually estimate this integrals and I mean the measure and then show that this is like the derivative, right? This is the difference. So, it is like the derivative. So, that will be like t to the n minus 1 and there is a t to the n in the denominator. So, that will go to 0. So, that is all, right. So, I have proved that if I take two arbitrary points x1 and x2, ux1 minus x2 is 0. So, this implies u is a constant. Okay. So, bounded harmonic functions are constants. Okay. So, we have one more property of the harmonic functions called the reflection principle. Again, this is something you have seen in complex analysis. You can reflect with respect to a line or a sphere and so on, and you get another holomorphic function, right. So, it is essentially the same principle, okay, and proof is sort of straightforward like what happens in. So, common area goes away, right, because it is the same function. So, if I take these two balls, the symmetric difference is this set minus this set. So, that is this area union this set minus the original set. So, that is this area. Yeah, so this is the union, right. This is the symmetric difference of this set with this set. So, let us call this set A and this set B, then this is just A delta B is A minus B union B minus A, right. That is just a notation for symmetric difference. So, is there a problem? Yes. Oh, I see. Okay. All right. Yeah. Thank you. So, what you can do is you can take the modulus here. Okay, is less than or equal to. Fine. Yeah. Thank you very much. Yes. Correct. So, well, what his point was, there is a integral over A minus integral over B. Okay. So, you may get integral over this portion minus the integral over this portion. Okay. Then only you have equality. Okay. Yeah. Sorry. So, instead of equality, we need only an inequality. So, you take modulus inside and you are integrating over a bigger area. So, there is no problem. Okay. So, you can put a plus there if you like. So, okay, but the proof is still the same. Okay. All right. So, we have proved Liouville's theorem, and let's write down reflection principle. Reflection principle is again something which you have seen in complex analysis. So, suppose D, so I'll write down, this is a slightly long statement, R n plus 1 is a domain symmetric with respect to Rn, symmetric with respect to Rn. What does that mean? That is x comma y in D. So, here x is in Rn and y is in R. Okay. If and only if x comma minus y is in D. Okay, symmetric with respect to Rn, right. let u equal to u defined on d plus. So, what is d plus? D plus is the positive part of the domain in d y positive. Anyway, when we draw the picture, this would be much clear. To, let us say, the real line be harmonic, okay. Define u on d minus by, so what is d minus? So, this is equal to all x comma y in d such that y is less than 0, right. That is the reflection of the above set by u of x comma y equal to minus u of x minus y and u equal to 0 on Rn intersection d. Okay. If u is continuous, then u is harmonic. Okay. So, if it is confusing at the first sight, please do not worry, I will draw the picture and tell you what is happening. D is a domain in Rn plus 1. So, we will do everything in n equal to 1, so that it is clear. So, I have R2, right, Rn plus 1, R2 is a domain symmetric with respect to Rn. So, symmetric with respect to the real line. Okay. So, what does that mean? That means if I take the domain and a point there that belongs to D, if and only if you can reflect with respect to the last coordinate, right, with respect to the real line. So, if I take a point here x comma y, this belongs to D if and only if the corresponding reflection here x comma minus y, right, this should also be in D, which means whatever portion is there above the real line, you reflect it, you will get the, right. So, it has to be a symmetric domain, right, something like this, right, whatever is here you reflect. Of course, it does not have to be a ball, it can be, it can be something like this, right, and then you can appropriately reflect it. So, you will get something here, right. So, domain has that property. I have a harmonic function here, okay. So, this is where u is and I reflect it. So, at this point x y, well, what do? I go to the corresponding reflection. So, that is x comma minus y, right, evaluate u here and the value of u here to be minus of that, okay. U of x comma y is, so on d plus, so this is the d plus part, right. So, this is d plus and this is d minus, okay. On d plus I know u, right. So, take a point in d minus, which is the reflected part, you go to d plus by changing y to minus y, evaluate u there, put a negative, that is the value. So, that defines u here in d minus and define u to be 0 on the line, because if it is negative, I mean, it is like odd function in y. So, it has to be 0 here, right. So, this gives me a new function on all of d, okay. If it is harmonic here and it is continuous everywhere, then it is harmonic everywhere, okay. That is the theorem, okay. So, the extra continuity part is something you should keep in mind, because u is 0 here forces, I mean, you could be a constant here, for example, non-zero constant, you can define its reflection here, but it is not going to be harmonic everywhere unless it is a 0 function, okay. It can be 1, it can be minus 1 here, it will be harmonic here, but if I include this and look at the bigger domain, it is not going to be harmonic, okay. So, the 0 here plus continuity in the whole domain, that is necessary, okay. Now, proof is staring at the board, okay. I do not need to write down anything. Well, what do? Here it is harmonic, fine. Well, here u of x y is minus u x minus y. To prove u is harmonic, you differentiate it twice. You will get the derivative of u upstairs, that is 0, and that's it. So, on the open parts there is no problem. Problem is with these points. At these points it is 0, but I know it is continuous. So, if I have a continuous function, it is enough to check mean value property, right. So, only at these points, because here and here I know it is it's harmonic. So, I take a point here, I look at the mean value. Well, how does the mean value look? You look at the sphere around that point. But the value of u here is the negative of the value of u here. So, integral is 0, right. So, on all these points you have mean value property. So, u is harmonic, okay. So, that is all is there. Even though the statement is very long, the proof is very simple, but we have to use it at some point. But I'll not get into too much of detail. So, we will see where all this come up in Fourier analysis. So, let me state a theorem and then we will stop. Because all the properties of the harmonic functions we need will be used here, but I'll state the theorem for the simplest case n equal to 1. The same proof works in all dimensions except for some slight modifications, okay. So, we start with what is known as the Poisson kernel. Poisson kernel. So, this is Py of x. So, this is 1 by y, 1 by pi x square plus y square. Where is x and y? X and y belong to R2 plus. Okay. So, this is the upper half plane, x comma y in R2, y positive, right. So, whatever is here, okay. This is harmonic here. First, you have to differentiate and see it as harmonic, or you can also write down a holomorphic function whose real part is this, okay. So, right, this is mod z square and that is the imaginary part of z. So, z by mod z square, that is like 1 by z bar or 1 by z, and 1 by z will be holomorphic, okay. So, anyway, I will leave it to you, check that it is harmonic in the upper half plane, okay. So, now everything is 2 variable, okay, x and y, okay. So, now I can set the theorem, let f belong to Lp of R. So, in general it will be Lp of Rn and there is a corresponding Poisson kernel, okay. Lp of R 1 less than to p less than or equal to infinity, okay. Let u x y be equal to f convolved with p sub y at x, okay. So, there are some things you should notice. So, I'll write down it here. So, Poisson kernel has various properties. Apart from being harmonic, you can think of y as a parameter epsilon, and this is simply the dilation, okay. So, let's write down that. So, one is Pyx, okay, equal to P of x comma y equal to 1 by pi y by x square plus y square is harmonic in R2 plus, okay. 2 Pyx is equal to 1 by y P1 of x by y, right. So, what is P1? P1 of x is 1 by 1 plus x square, right, by 1 when y is equal to 1, right. So, you look at this function 1 by 1 plus x square, dilate it, right. So, what do? You do an x by epsilon 1 by epsilon to the n, right, but n is 1. So, 1 by epsilon. So, that is precisely this, right, 1 by y P1 x by y. So, it's one function dilated by y, okay, where y is positive. That gives me a function of 2 variables, right, x and y on the upper half plane. It is harmonic there, okay. So, you can check that integral of P1 x dx is 1, okay. So, I am taking a function whose integral is 1. So, this serves as an approximate identity, okay. It is a positive function whose integral is 1. So, because of this, f convolved with py will converge to f in LP at least for p strictly less than infinity as y goes to 0, right. Epsilon goes to 0, here it is y. So, it works as an approximate identity. Okay, that is important for us. Okay, so now I will complete the statement of the theorem. Okay, so A, then u of xy is harmonic in the upper half plane in R2 plus. So, take any LP function, convolve it with the Poisson kernel. So, you can convolve with the Poisson kernel. So, remember this is the function and you are dilating, right. This function belongs to L1 intersection L infinity of R, right. It is integrable because it is like 1 by x square at infinity and it is bounded. So, it is in L infinity. So, it is in all LP. So, I can convolve with any function, right, in LP, because LP convolved with LQ goes to C0 and so on, you have seen that. So, convolution makes sense and it will be harmonic in the upper half plane. Okay. So, starting from an LP, arbitrary LP function, convolution with the Poisson kernel gives me a harmonic function in the upper half plane, but it has some property. Okay. And supremum over y greater than 0, norm of u dot y, LP norm, right. This is less than or equal to LP norm of f. Okay. This is straightforward because u is simply f convolved with py, right. So, if I fix y and take the LP norm in x, I am taking the LP norm of the convolution, right. F is in LP and this is in L1. So, convolution makes sense, this will be in LP. LP norm of this is less than or equal to LP norm of f times L1 norm of this, remember that from yesterday, but L1 norm of this is 1, the integral is 1, right, it is a positive function. So, I will get this for any y, so I can take supremum over y. Okay, so, that is a trivial statement. You have to prove that it is harmonic. How will you prove that it is harmonic? Well, P is harmonic, write down the convolution, right. So, there is P there, prove that it satisfies the mean value property. Well, how will you prove it satisfies the mean value property? You integrate over the sphere, interchange integrals, put the integral over P, but P is harmonic. So, that satisfies the mean value property and that will be. Okay. So, it is just 2 lines, but yeah, write down with details so that you know when to interchange integrals and so on. So, one way is trivial. The main theorem is the converse, that whenever you have a harmonic function with some property like this, it actually comes from a Poisson integral. Okay. So, B conversely let u be harmonic in R2 plus, so the upper half plane, such that supremum over y positive, the LP norm of in the first variable, right, this is finite. Okay. Then for 1 less than p less than or equal to infinity, uxy is f convolved with py of x for some f in LP. Okay. So, okay, and the norm of u comma y minus f LP norm goes to 0 as, so this is simply approximate identity property, right, there is nothing there, but I will tell you 2 more lines and then stop. Look at the theorem again. If I start with an arbitrary function f in LP, convolving with the Poisson kernel gives me an harmonic function in the upper half plane with some bound on the LP norm. Okay. So, bound depends on which p it is and you have f LP norm of f on the right hand side, but this is sort of a trivial statement, in the sense it is easy to prove, because this is a convolution and convolution with a harmonic function, right. So, you will get a harmonic function and this works as an approximate identity. So, LP norm of this is less than to LP norm of f times L1 norm of this, which is 1. So, you will get this. Main part is the converse. I take a harmonic function with this property that it is finite. Then I can get an f in LP such that u is the Poisson integral of f, which means it is the convolution of f with the Poisson kernel. So, but remember the range, okay. Here all p was involved, here p equal to 1 is not there. For p equal to 1, the result is not true that you can get an f in L1, you will get a measure. So, I will explain that after we do this. For p strictly greater than 1, any harmonic function with this property is the Poisson integral of some function in LP, okay, and this converges. So, the convergence property is the property of the approximate identity, okay. There is nothing here because this becomes f convolve with py and f convolve with py converges to f as y goes to 0, right. That is one of the things we observe. But what I want to say is this solves what is known as the Dirichlet problem for the upper half plane. So, if I look at the upper half plane, okay, so Dirichlet problem is the following. It is a PDE question. So, find u, so find u such that the harmonic delta u is 0. So, that is the Laplace equation and on the boundary it takes the prescribed value, right. So, if I give you f here, can you find an harmonic function u such that delta u is 0 and on the boundary u satisfies u equal to f. So, u will have to be equal to f on the boundary, right, on the boundary of R2 plus, okay. So, this is well understood in the case of bounded domains and so on. This is one such unbounded domain where there are no uniqueness results, but for certain kind of harmonic functions one has something, okay. So, this solves the Dirichlet problem. If I give you f in LP here, I can look at f convolve with py, that will give me a harmonic function. As y goes to 0, I will get back f. So, u equal to f on the boundary in the sense that u as y going to 0. So, those are radial limits, right, those are sort of lines perpendicular to the x axis, right. On these lines it will converge to f, okay. If I take some curve like this and see if it converges, it may not, okay, but we have proved only boundary, radial, what are known as radial limits, okay. So, we will stop.